Okay, hey, looking at section 9.4, I'm going to have to make this quick because I've got an event I've got to run to in about 15 minutes. So I'll give you a few and we'll go with that. We know that there are indefinite integrals and there are definite integrals where we have the bounds. And we've worked with integration on those two types. What we're looking at in this section are improper integrals. You're going to see integrals where we are trying to integrate to infinity. So in this case, we're going from a to infinity. What we'll do is replace infinity with just a value, say b, and then I will include this extra thing, the limit, as b goes to infinity. So what I'll do is we will evaluate the integral from a to b, and then once I get that answer, that numeric derivative, it will have variable in it though. From there, I will work back and look at the limit allowing b to go to infinity. Okay. What if the infinity shows up in the bottom of the integral where we're going to negative infinity? Well, then it'll be kind of similar. I'll replace negative infinity with an a and then add on the fact that I'm going to look at the integration. After I'm done, I'll look at it from the lens of a going to negative infinity. So it's a workaround. It's a workaround, trying to make a definite integral where we were going to infinity or negative infinity. There might be times where you'll have improper where we're going from negative infinity to positive infinity. In that case, we're going to break it up into two separate integrals. One easy place to separate, they're suggesting c here, but I might even suggest that we look at, going to 0, a to 0, and then pick up at 0, go 0 to b. Just because 0 is such an easy place to integrate, and evaluate. An improper integral is said to converge if the limit exists. If the limit doesn't exist, it is said to diverge. Okay, so an example of one. Let's look at, I'm going to look at this one here. So the integral from 1 to infinity, obviously it is improper because we're going to infinity, so this will be the limit as, I'm going to say b goes to infinity from the integral of 1 to b, and replace infinity with b there, x to the negative 2 dx. So I will integrate that, and I still will have my limit as b goes to infinity to deal with. But first off, let's work on our integral. It'll be negative 1 over negative 1, evaluated 1 to b, and pass through to our fundamental theorem. And b will go in. This will be, because this will be a negative 1 over x, right? Get that to erase. This will be the same as negative 1 over x. Okay, so plug in b, I'll have negative 1 over b minus negative 1 over 1, which makes it a plus 1. And now if I evaluate the limit part, 1 over b heads to 0. And I notice then that the limit of 1 is 1. The limit of a constant is the constant. So I get an answer of 1, which it says that there is a limit. So this is known to converge. We could actually calculate the area under the curve, even though we were headed to infinity, which means that this function was decreasing quickly enough that the area ended up having a finite amount. If I had done this one, this actually has a limit going to infinity, which means it diverges. So just this little bit of difference, squaring an x over having 1 over x, this one races to its asymptote fast enough. And that's kind of vague, but that's kind of the idea. Determine whether it converges or not. Same idea on this. We could integrate and replace it. So why don't I do this one here? The limit. As b goes to infinity, replace infinity then with b of 1 over x minus 1 dx. And that will give us the limit as b goes to infinity of natural log absolute value x minus 1 evaluated from 2 to b. And that would be the natural log of b minus 1 minus natural log of 2 minus 1. All of this I'll take the limit of, but I think there's still a little bit of simplifying to do. So the limit as b goes to infinity, the natural log of 1 here would be 0. So this will just evaluate to natural log of b minus 1. Now allow b to go to infinity because we had that improper integral. So we would be thinking kind of infinity here. The natural log of infinity would be infinity. Therefore, this is diverging. And I just thought of a good reason why we should do problem C, so I'm going to step back and do C, because this one, no, it's not this one. I'm sorry. Where is it? This is the one I want to do. Yeah, definitely. 1 plus x squared rather than 1 plus x, quantity squared. Whoa, we got interesting stuff going on here. I'm going to break this at 0. So I'm going to have a limit as b goes to infinity. I'm going to deal with the upper bound here first. So 0 to b, replace that with b and use the limit. And I'll have 1 over 1 plus x squared dx added with the limit. I'll use a different variable. Let's go with a, and that'll be the integral from a, because we're replacing with negative infinity there, negative infinity up to 0 was my break point. So 1 over 1 plus x squared dx. Hopefully you remember and recognize this has a nice integral. It's tangent inverse. So this will look like the limit as b goes to infinity of tan inverse of x evaluated from 0 to 2 plus the limit as a goes to negative infinity of tan inverse of x evaluated from a to 0. Okay, let's do our fundamental theorem work next before we talk about the limits. So keep writing limit because I haven't evaluated any limit yet. 2 goes in and I get tan inverse. That was not a 2. Shouldn't that be b? Where did I come up with 2? That's a b. Okay, b goes in and then I'm minus tan inverse of 0. That is the first limit problem. Second limit problem allows a to go to negative infinity. Plugging in 0, I'm going to have tan inverse of 0 minus tan inverse of a. Now evaluating the limits. Okay, so this is where I think you might say like, oh boy, I don't remember this stuff. If we had infinity there, we'd also have negative infinity here, and those are going to erase. So let's do it differently. Infinity and negative infinity is the idea. So do you recall your tangent function? Tangent function had a couple asymptotes going on the pi over 2, so negative pi over 2 to pi over 2, and then my tangent function did this. All right, that's tan x. But I need tan inverse. So I suppose I could read this graph backwards, but instead I'm going to plot out the inverse function. Well, now these bounds for the domain become asymptotes on the range, doesn't it? So I have an asymptote here at y equals pi over 2 and y equals negative pi over 2, because remember your domain and range just flip-flop on this. So now my function's going to be this number. This is tan inverse of x. So What is the tan inverse of infinity? Well, that infinity, where x is equal to infinity, would be clear out here to the right. And that puts me up along my asymptote. So this actually evaluates to pi over 2. The other way you could do this is to work backwards and say, you know what, when do I achieve infinity? Here, what input gave me that? Pi over 2. So it just kind of depends on which route you come into it from, but I think probably safest way is to think of your tan inverse graph. Tan inverse of 0 is still 0, so this will be a 0 here. Tan inverse of 0 is 0. Tan inverse of negative infinity. Well, negative infinity is out this direction, and so as I head out to negative infinity, x driving towards negative infinity, we're riding along the asymptote of negative pi over 2. So this will evaluate to negative pi over 2. I'm going to erase this stuff because the problem needs to be evaluated here to finish up. All right, so we got a limit as b goes to infinity of pi over 2 plus the limit as a goes to negative infinity of negative pi over 2. Well, the limit of a constant is that constant. So we get pi over 2 makes a full pi. Half pi plus a half pi makes a whole pi. There we go. This one we could use integration by parts. It is a nice one that you can actually, we can see that if I take a derivative and keep taking a derivative, eventually I go down to 0. So how about tabular method for this one? You know, U sub wouldn't work, but tabular method is a great option. A little faster than doing the official, you know, UV, UdV minus VDU type thing. The integral of that. Alrighty, getting late, guys. So I've got x, the derivative of x is 1, the derivative of 1 is 0. Remember how the first column we're taking derivatives. I selected kind of my u to be x. Then my next column, I'm selecting my, what was it, u dv minus the integral of v du. So this is going to be, this was my u, this is acting like the dv. So I've got to integrate this side. There's the negative e to the negative x, and then integrate again, and we're there. Connecting up on the diagonal, starting with a positive and a negative then. Put it together in this integral of x e to the negative x dx turns out to be x over e to the x, negative exponent drops it to down below. That was a positive, and this next one, hold it. I think I looked wrong, guys. I didn't follow the first arrow. So that's going to be a negative x over e to the x. And then following the second arrow, this has a negative, so this is also going to be minus 1 over e to the x. So there's its integral. Now I'm going to have the limit as x goes to, not x, as b goes to infinity, because we're going to replace this with b, and we want to integrate from 1 to b of x e to the negative x dx. That would turn out to be the limit as b goes to infinity of the integral we just got done calculating using the tabular method, evaluated from 1 to b. Limit as b goes to infinity. Let's start at the top. We'll get negative b over e to the b minus 1 over e to the b, first part of our fundamental theorem, minus the bottom. So now we're plugging in 1. We'd have negative 1 over e minus 1 over e. All right. Well, now we got to evaluate at infinity. I'm going to start with the easy ones. Okay, so if I'm going to infinity here, This would all go to 0. This would be negative 2 over e, which would come back to be plus. I think the thing I was avoiding is, what do I do with this, right? I've got infinity over infinity case. So if I took the derivative and thinking that this really is a number, right? It represents a number. Well, its derivative would go to 0. But e to the b would continue to be e to the b, e to the b to the b. That's kind of a bad way of phrasing this, but another way to look at it is e raised to infinity is going to grow more quickly than just b going to infinity. And for that reason, the growth rate of the bottom is faster than the top. I know that this is going to 0 then by the growth rate comparison. So I want to get a 0 there, and the limit as b goes to infinity, I would end up with 2 over e, because I end up with the limit of a constant here. So 2 over e. Kind of a tough one. Kind of fun to use tabular method again, though. This is a partial fractions one. We would work with partial fractions on this. Let's set it up. Let's go b, limit as b goes to infinity would be a way to rewrite this. I'd have something over x plus 3 plus something over x plus 2. Is this coming back to you? And then we do the a, b idea here where we're trying to find the two values. And I believe if you did your work on this, you would find out that my little a in this case turns out to be -1. And a little b on this one turns out to be +1. And then you know how to go forward from there, I hope. The limit of this, or the integral of this first one would be a natural log. We get the negative out front of absolute value x plus 3. It's very nice and clean because we just have one x, so that made that simple. And the integral of the second fraction would be also a natural log absolute value x plus 2. Of course, we still got to do all the limit work, and we got to do the definite integral from -1 to b. Little bit more simplifying before I go into fundamental theorem. I would put these together using one natural log, and that's going to come together as a quotient. Here's my positive term, so that's going to go on top. This would be minus, so it's like the negative term, negative power coming down below. So evaluate this from -1 to b, and start with b, go on top, and finish that up. The answer turns out to be, once you get it done, 0 minus the natural log of 1/2, which turns out to be negative natural log of 1/2. But there's many ways to write natural logs. Always, this would be thought of as 2 to the -1. Bring this power back up, and not 2 to the -1. How about 1/2 to the -1, which then spreads -1 power to each of them. And the bottom line, that's a 1 to the -1, is this becomes natural log of 2. All right, hopefully that helped you guys. I kind of did it quickly, and we did a Math Excel assignment on this. See you tomorrow.